Okay, hi, I'm Amanda Olson, and we're going to be looking at section 1.3. One of the things I would recommend is just to have a calculator handy, and I also recommend finding this PowerPoint that is attached to this video. Section 1.3 deals with evaluating limits analytically, so that's what we're going to discuss. A limit is a way of evaluating a function at a value for which the function may or may not be defined. So when we talk about functions, sometimes they have a domain and sometimes they don't. Or they all have a domain, but they have certain values that aren't within that domain. And with limits, we can say, what would we expect the function output to be for certain values that might not be in the domain? If we can just substitute our limit value into the function, then that's called direct substitution, and it's a pretty simple limit to find. So here this problem reads the limit as x approaches c of f of x. And so this is asking what, as x gets closer to c, what are my f of x or my y values? What are my output values getting close to? And for standard functions, polynomial functions, linear functions, you can just substitute c right in there, and the limit is exactly what the function value would be. There's no guesswork. If that's the case, we would call that function continuous at c. So some basic functions that we have the limit of a constant function. So for example, if this was the function y equals b, then its limit as x approaches c, well, the output is always b. So the limit is going to be b as well. We would expect for any input the output to be b. For the identity function, something like f of x equals x or y equals x, the output for this function is exactly the input. So what we would expect as x gets closer to c, we would expect the output to be approaching a c value as well. And then same if we have a polynomial. So one example might be if I had y equals x squared, then direct substitution is possible for that limit as well. N can be any constant positive value. So here we want to look at finding some limits. I'll just go ahead and change my color. So here the first one, we're looking at the function, it's not listed, but you could think of it as y equals 4 or f of x equals 4. So if you were to graph that, regardless of what our input is, our output is consistently 4. So as x is zooming in on 4, or 2, we would expect the outputs of f to consistently be 4. Here, again, this is that identity function, y equals x. So what we would expect for this one is just direct substitutions possible. This limit value is equal to 2. For this one, we would expect it to equal 3 squared. Again, the limit is not very interesting if direct substitution is possible. If the function that you're considering within the limit is defined at your value for c, then your limit isn't really interesting, and direct substitution is often possible. So we have lots of properties of limits. We can multiply a limit by a scalar multiple. So if you have a function times some scalar multiple, you can factor that out and just find the limit of that function as x approaches c of the scalar multiple. You have some sum and difference properties. So sum and difference holds under limits. Products hold within limits. Quotients hold within limits, so long as that when you directly substitute c in for x, you don't have any undefined or zero values in the denominator. And then you also have exponentials are defined under limits as well. So using all of those, we can evaluate this limit. And this is just the basic limit of a polynomial. When you're looking at limits, there's a couple techniques you want to try. The first thing that I always try is just, can I directly substitute my c or my limit value into the function? If I can, that's usually going to be the limit. So I look at, can I directly substitute? And our function that we're dealing with is f of x equals negative x squared plus x minus 2. And so definitely I can input 2 in for x into this function. So we have minus 2 squared plus 2 minus 2. So then this gives me negative 4 plus 2 minus 2. And we have this equal to negative 4. So this limit not only exists, but it equals negative 4. Okay. So that's kind of our end result. The limit equals negative 4. In this case, that happens to be the f of 2 value, but that won't always be the case. So the limit as x approaches 2 of the polynomial function is simply the value of the function at x equals 2. This direct substitution property is valid for all polynomial and rational functions with non-zero denominators. So if we have a polynomial function or a rational function, and in case you forgot what a rational function looks like, that root word in rational is ratio. And so it's something like an r of x equal to an f of x over g of x. So some people think rational, fractional. It's essentially a fraction, algebraic fraction is a rational function. And of course, the denominator can't be 0. So if it's a rational function or it's a polynomial function, either way, direct substitution is possible. So evaluating that limit isn't very complex. So for this one, I look at, can I directly substitute? And I'm considering negative 1. And I have the function that I'm dealing with is f of x equals x squared plus 1 over x. And I just consider, I'll move it down here. Can I input negative 1 into that function? And if I can't, then I have to look a little bit harder to find that limit value. So I do that here. Negative 1 squared, negative 1 times negative 1 is going to be a positive 1 plus 1 over negative 1. So we end up with 2 over negative 1, which equals a negative 2. So it is defined, and as a result, then we can see that this limit value is equal to negative 2. Oops, there we go. Polynomial functions and rational functions are 2 of the 3 basic types of algebraic functions. The next theorem deals with the limit of a third type of algebraic function, one that involves a radical. So if we're dealing with an even root radical, for example, 2, so like a square root or a fourth root, any kind of even root, and c is some value greater than 0, this is just going to be exactly the same as direct substitution. It gets a little bit more complicated when n is odd. If n is odd, direct substitution is only possible if c is just some real number. So as long as it's a real number, then direct substitution is possible. We also hold that limit of composition of functions holds. So the limit of f of g of x is going to be f of the limit of g of x as x approaches c. So find the limit of g of f of x. So one of the things is you could find that function if you wanted to. You could look at, well, what is g of f of x? So this is going to be g of an f of x. We have x squared plus 2. And then the g function takes it and says, okay, takes our input, x squared plus 2, and then it adds 7. So then this becomes that function, the square root of x squared plus 9 when we combine like terms. So we could write this as the limit as x approaches 0 of x squared plus 9. If we didn't want to find that function, and it kind of depends on, are we evaluating this limit at various values of c, or do we have only one value of c that we're considering? If we have only one value of c that we're considering, it's, as we do in this case, it's probably best just to use that property of limits. So that property of limits that we had on the previous page said the limit as x goes to 0 of g of f of x is equal to g of the limit as x goes to 0 of f of x. And since f of x is defined at 0, this is just going to be equal to g of f of 0. We can directly substitute 0 in, and what we end up with for this is g of, if I substitute 0 into this function, I get 2. So then here I have the square root of 2 plus 7, which gives me the square root of 9, which gives me 3. Going back to what we had above, this is still 0 substitutable. I would get the square root of 0 squared plus 9, or the square root of 9, and I would get 3. So there's kind of multiple ways you can do this one. It just depends on what you're looking for. If you're only evaluating the limit at one distinct value of c, so in this case, we were only looking at it as x approaches 0, okay, then probably using that theorem that we had is more convenient. If I was going to be changing it and looking at the limit as x approached 1, the limit as x approached 2, the limit as x approached 3, and kind of have multiple limits I'm evaluating, it might be best just to find this function instead of reapplying that theorem every time. But either way is completely correct, and it's not wrong to evaluate it, using any of those methods. So we've seen the limit of many algebraic functions can be evaluated by direct substitution, and the 6 basic trigonometric functions also exhibit this desirable quality. So that's really nice if we're dealing with the limit of sine of x. As long as c is in the domain of each of these functions, direct substitution is possible. And so functions like sine of x, of course, the domain spans all reals. When you start getting into tangent of x, remember that tangent of x, because tangent of x is equal to sine of x over cosine of x, you have certain values that you can't input. In fact, you can't input values that make that denominator equal to 0. So that's going to restrict your direct substitution values a little bit. Same with secant and cosecant. Those are going to have restrictions on your specific values. But as long as c is in the domain of your given function, direct substitution is possible for the trigonometric function. So for this function, cosine is defined all over the reals. So I know that this limit exists, and it's going to exist as direct substitution. So I'm just going to substitute in x equals 1. So this is going to be cosine of pi. And if you're looking for a unit circle, there is one at the bottom of the modules page in Canvas, and definitely feel free to use that. Otherwise, I would say hopefully you kind of have some of this committed to memory, but I also understand that sometimes it's been a little while. If you do have to use a resource here, that's fine. I would just say, this kind of might be something for you to jot down of, hey, I need to refresh myself on finding these values. So cosine of pi is 180 degrees, so that puts us at that left value, and then of course this is the x value, so that's going to be a -1. So this limit exists and it equals -1. Another theorem that we have, and another type of limit situation that we encounter, is maybe one where direct substitution is not possible at that specific c value, but the function's defined at all values except that value of c that you're looking at. So what does that look like? If I had a function like y equals 1 over x, this function's defined on all values except x equaling 0. That's the only value where direct substitution wouldn't be possible. But since this is defined, the domain of that function is equal to, -infinity. It's in the set from x not equaling 0. There's only one value. It's defined over all the reals except at one point. So this is where f of x and g of x are equivalent except for one value, all but one point. That one point in this case is 0. So we can say that 1 over x equals 1 over x, or we can find some equivalent function. And they agree at all but one point, then the limits of the two functions are going to agree. Okay, so we'll see that in this example here. So one of the things I would always recommend trying, first of all, when you're looking at limits, is just, does direct substitution work? Okay, so I go ahead and I look at substituting -2 in for x. And when I do that, I get -8 when I cube that, plus 8 over -2 plus -2. That's going to give me 0. And this is then at that point undefined. Okay, we'll look at a little bit later, whether it be in this course or calculus 2, indeterminate form, that 0 over 0 form. But as of right now, as soon as we see that 0 in the denominator, that tells us that direct substitution isn't possible. So our next technique is to see, can we find a function that agrees with this, except for maybe when x equals -2. And the way that we do that is usually by reducing this expression. Okay, and so I see that this is a sum of cubes. So if you need to take a second to pause the video and refresh yourself on factoring, factoring is going to come up. So just if you need to pause the video or make a note, hey, review factoring. But this is a sum of cubes. And so it factors to be x plus 2. And then we have x squared minus 4x plus 4. Let me check that out here. Okay, this should be a -2. And I should say, and this is random, but if you hear some snoring in the background, I have a pug dog and she just snores, and she just feels comfortable being in my office whenever I'm doing anything. So just ignore that. It's not a person or a bear or anything. It's just a dog. Okay, so then when I look at this here, after I've factored the numerator, I can see that, well, I do have a common factor in the numerator and denominator. And the property that allows me to divide these does have the condition. It's essentially the multiplicative identity function. You're doing this a lot of times without even thinking about it because you've been doing it so much in algebra, but you're essentially multiplying the numerator and denominator by this 1 over x plus 2, 1 over x plus 2. Okay, well, the problem here is that we're assuming then x does not equal -2. Okay, so this function, if we assume x doesn't equal -2, then we can cancel those values out, and we end up with x squared minus 2x plus 4. And so this function we can call g of x. And I want you to recognize that g of x is equal to our f of x of x squared plus 8 over x plus 2. They're equivalent except when x equals -2. Okay, so what that means then, if we go back to that previous theorem, since these two functions agree at all except for one particular value of x, in this case it's the value of x where x equals -2, then their limits are going to be equivalent. So then here we can erase all this and we can just look at, we know that this is going to be equivalent to the limit as x approaches -2 of this function x squared minus 2x plus 4. And then we can just see if direct substitution is possible now for this, because I think this is defined for x equaling -2. It is a polynomial. So I input -2 in for x. I apologize for kind of getting congested here at the end. We have -2 squared is 4, -2, -2, we get plus 4, plus 4. This limit value ends up equaling 12. Okay, so always try direct substitution first. Your next goal is can you find an equivalent function that agrees at all but one point? That should be your second technique. And we can see that here. So looking at this graphically, if you were to graph, and if you're looking for really nice graphing software, if you don't have a graphing calculator, which is not required, Desmos.com is great. You can't use it on exams, but it is really good as far as graphing. I think it's pretty user-friendly. It's free, it's a website, and it's an app. I really like it. So here we have this function, and if you graph it on Desmos, it's going to be too zoomed away that this is going to look like a closed circle. But if you really just kind of zoom in, you'll see that it's an open circle. It's a little bit more exaggerated on this picture. But you can see that this is the graph of f of x, and then this is the graph of an equivalent function, except this function now is defined when x equals -2. And so then we can see, okay, well, what is going to be the output? We found it was 12, so I should make my graph a little bit better. So you can evaluate limits graphically as well. And I would just encourage you, though, to be careful when you look at it graphically. Make sure it's defined at that point. You really want to zoom in. So the basic way for finding limits is, first off, look at if direct substitution is possible. If direct substitution is possible, okay. If you can't, then look at, can you simplify the function to an equivalent function where you can directly substitute. Okay, so that was like in that last example that we saw. After that, if you can't do it, sometimes you look at limits that are approaching infinity or -infinity, or you're looking at x not approaching a specific value, or the function's not approaching a specific value. Then you want to use a table or graph. So you can definitely look at a table. You can graph, x and then f of x. And let's say in this case, we are looking at the limit as x approaches c of f of x. I think what we're going to do actually is we're going to stop here, and we'll hold off on this for our next video. So that'll be the part 2 video, and we'll look at kind of finishing this up. Thank you.